Alright nerds, so here we have Newton's second law of motion, and over here we have an extremely famous painting of Sir Isaac Newton from the mid-17th century. So that's what he looked like with his rad metal hair, and we can break this down into two ways. We can do it in words, or we can do it in maths, and we're going to do both. The words part seems a bit easier, and then we're going to do it in numbers, and that's the part I really need you to focus on. So first off, basically an object is going to accelerate if an unbalanced force is applied to it. In other words, if a force applied to it is bigger than any of the other forces, it will move off in that direction. So its acceleration will depend on two things: the size of the force applied to it and the mass of the object. Okay, so if we break that down, we can do it mathematically, whereas F equals ma. You've seen this before. So F is force, m is mass, and a is acceleration. You've seen this formula before, but this is what it means. So basically, this mass will accelerate if a force is applied to it. Now, we can rearrange that to find those different numbers. For example, if we know the force and the mass, and we want to find out how something's going to accelerate, we rearrange it to this. And if we know the acceleration and we know the force, so we can use that to work out the mass of an object, as we have right here, we can rearrange the equation for that. Now let's see what that looks like. Okay, so here we have one dude and he's playing basketball. And here we have the same dude still on the same basketball court pushing a car. Why it's on there, I don't know, but that doesn't matter. So basically, if we look at the arrows, we can see that the force applied here is the same as the force applied there. What's different? The difference is the mass. In this case, back we go. He's applying it to a ball and he's applying it to a car. Okay, so what you'll see is the force is the same, but the acceleration is much, much different. So the acceleration for the car, it's tiny, whereas the acceleration for the ball is quite large. Don't worry about this so much, but all it's saying is that the way you would draw this diagram just for the vectors, remember we talked about drawing forces, they look roughly the same because the force stays the same. The acceleration, much, much smaller. Alright, so here we have an elephant and a tiny little alien thing. Both are falling due to gravity. Now, you remember from year 7, whenever two objects fall due to gravity, they fall at the same rate. So you could have a car and you could have a mouse, and as long as there's no air resistance, they're both going to fall at the same speed, or fall at the same acceleration. And what that means is the force due to gravity must be different. So here we can see it broken down in two ways. We have acceleration equals force divided by mass, so 10,000 divided by 1,000, 10 meters per second per second. Here we have 10 newtons divided by 1 kilogram, and we're down to 10 meters per second per second. Again, acceleration is the same. And with gravity, it always is. Okay? Alright, so that's it. I'll see you in class and we'll play around with this a bit more.